And this talk will be entitled Virtual Blue Noise Lighting. The authors are Tianyu Li, Wenyou Wang, Daqi Lin, and Yuksel from the University of Utah. And Tianyu and Wenyou will be giving the talk.
Hello everyone, I'm Tianyu from University of Utah. I'm glad to be here to share our paper, Virtual Blue Noise Lighting, with you. My co-author Wenyou is another first author of this paper. Here is a group of images comparing our method to prior virtual light methods using VPL, VSL, and rich VSL. As you can see, our method can render the clearest glossy reflection on the box behind Buddhas. We achieve this by improving virtual light placement, distribution, and sampling and emission profile computation. Before introducing our method, let's recap the prior work on virtual light methods. Rendering with virtual lights, also known as instant radiosity, is a two-pass algorithm. In the first pass, we trace random light passes and place virtual lights at each vertex along these light passes. The second pass is final gathering. Indirect illumination is handled by computing direct illumination from all virtual lights. Conventional VPL cannot properly handle specular transport. We can solve this problem by using virtual spherical lights. VSL distributes the energy over nearby surfaces inside an imaginary sphere. This removes the singularity of the geometry term, but it also leaves a co-integral to solve, which can be costly. Using VSL does not produce splotches like VPL with specular transport, but the results of VSL can be blurry. Rich VPL is a more recent technique to improve specular transport using virtual lights. For rendering more challenging situations like this scene, rich VPL uses virtual lights with emission profiles and compute emission profiles from a photon map. However, after adding direction emission profiles, a virtual light becomes very expensive, thereby limiting the number of virtual lights that can be used in practice. Considering this limitation, the virtual light placement becomes much more important. In our paper, we introduced various improvements to the rendering pipeline with virtual lights. As a result, our method provides a better illumination estimation and faster convergence during rendering. We identify three main problems in prior virtual light methods. Problem 1 is wasted virtual lights. These are virtual lights that have no contribution to the final image. For example, in the rich door scene you see here, there are very few virtual lights inside the room. This results in a poor illumination estimation, forming splotches you see in the rendered image on the left. If we step outside, you will see where all other virtual lights are. They are placed outside of the room and do not contribute to the final image. So this is an extreme example. It's not uncommon to have a large percentage of virtual lights with no contribution to the final image. Problem 2 is hot zones, where a significant portion of light passes go through are often oversampled with many virtual lights, even when their contribution to the final image could be effectively approximated using fewer virtual lights. In this example, a large portion of virtual lights are placed close to the original light source. Other areas are not sampled adequately. In our method, we address problem 1 and problem 2 by generating virtual lights starting from the camera. As you can see, this results in a much better sampling of the room. Problem 3 is that random sampling leads to many virtual light pairs that are placed too close to each other, which is another source of waste. Also, there are large gaps between virtual lights, resulting in a poor distribution of virtual lights. We address this problem by generating a blue noise distribution of virtual lights. This significantly improves the quality, particularly for glossy and specular surfaces. We address problem 1 and 2 by generating virtual lights starting from the camera. This ensures we do not waste space with unused virtual lights, and we do not place too many virtual lights around hot zones. We will address problem 3 using sample elimination to get a blue noise distribution of virtual lights. Note that some of these problems were recognized in prior work as well, but the solutions we describe are much more effective. Please see the paper for a more detailed discussion of prior work. Here is an overview of our virtual blue noise lighting VBNL method. It begins with generating initial candidates from camera. Then it performs parallel adaptive sample elimination for blue noise distribution. The next step is computing the emission profiles by tracing photons. Finally, we sample the virtual lights during rendering. I'm going to explain these 4 steps in this order. We begin with virtual light generation from camera. To address problem 1 and problem 2, we generate virtual lights from the camera. We start by tracing a camera array to find the primary hit position X, and then we can extend the path to get the position of a virtual light position candidate Y. This guarantees that all the virtual lights we generate contribute to the final image. In addition, the local density of virtual lights is proportional to camera importance. This addresses problem 2, the hot zone problem. The virtual lights we generate this way from a random distribution. Yet, these are not the final virtual lights. They are all the initial candidate positions. Next, we improve the distribution of our virtual lights to achieve a blue noise distribution using sample elimination. Let's say the difference between a random distribution and a blue noise distribution. Our target is to achieve a blue noise distribution with our virtual lights to address problem 3. We achieve this via sample elimination. First, we generate more virtual lights than we need. Then, we apply sample elimination to strategically remove some of them and achieve a blue noise distribution. So, with sample elimination, we eliminate some candidates. Then, we can get virtual lights with blue noise distribution. This is an example showing the distribution of initial candidates. Very dense, right? And after sample elimination, it's difficult to find any 2 virtual lights are still grouped together. However, using the same Poisson radiance disk is not always good. If you check the reflection of the bottles on the table, you will find that the reflection disappears. In that sense, uniform sample elimination can be worse than random sampling. So for rendering glossy reflection using virtual lights, we might want to keep the origin sample density, because the origin density contains information about camera importance. We will address this problem by using adaptive sample elimination. We will adjust the Poisson disk radius of each virtual light based on the initial density. With adaptive sample elimination, we can preserve the density of initial candidates. This preserves the glossy reflection in this example. In the paper, we also describe a method for performing sample elimination in parallel. Our parallel sample elimination splits the sampling domain into subdomains with equal samples. We use a balanced KD tree to partition sampling space. We begin sample elimination in the leaf nodes of the tree. Then, we merge them and continue sample elimination. For this scene, eliminating more than 1 million samples, parallel sample elimination is almost 10 times faster in a 12-core CPU. We have talked about how to get a blue noise distribution of virtual lights. So far, the virtual lights are just placeholders. They do not have any emission information. Now, it's time to compute their emission profiles using photon splitting. This step starts with photon tracing. Instead of storing a photon map, we generate each photon and find the virtual lights around the hit point, and distribute its energy to the nearby virtual lights. We call this process photon splitting. After that, we do not need to store the photon. This way, we can efficiently use a large number of photons for estimating the incoming radiance for each virtual light. We use a O'Hedron map to store direction incidence radiance information. After photon tracing, we have all incident radiance stored in such a hydro map. Then, we use a compute path to radiance conversion to convert the incident radiance to argo radiance. Argo radiance is stored in a hydro map as well. Here is an example incident radiance map. Let's convert it to an argo radiance map, which is the emission profile. This is a video clip showing that how emission profiles change during photon tracing. All our emission profiles are packed into a single texture called mega texture. After computing the incident radiance, we convert all incident radiance map to argo radiance map, representing the emission profile of our water lights. So we finished computing emission profile for water lights. Now let's talk about water light sampling. After computing emission profiles, we have our water lights with direction emission information. Next problem, how can we sample them efficiently? Let's try power-based sampling first. It's not surprising to say that power-based sampling cannot give us a good result. Then, let's try light beam sampling, which is a hierarchical sampling technique. Even with this, we cannot get much improvement. Can we do better? The answer is yes. This is a result of BSDF sampling. So, how can we achieve this? For BSDF sampling, requiring nearby water lights to decide the final light samples. When we pay its short distance ray tracing, which is very fast. This way, we get rid of explicit cone sampling for spherical lights. Also, instead of one light sample, we can use one BSDF ray to sample all water lights that overlap with the hit point. Compared with the light BVH and power-based sampling, BSDF sampling spends less time and the convergence is much better. We can even do better with multiple impedance sampling. Compared to BSDF sampling alone, we can get better results and only slightly increase the cost. Instead of MIS, we can also try to combine our sampling technique with raster. We can even get better results. But because of the overhead, we pay more computation time for raster sampling. If we use the same shading time, our MIS can generate better results. Now, we have our sampling strategy, but we can still encounter other problems. Especially, we may have undersampling problem. With highly specular material, we can clearly see these artifacts. That's because when we hit a highly specular surface, the specular lobe is narrow, so for this estimated area, we do not have enough water lights. Undersampling also happens near corners, as can be seen in this image. This is because if the shading point is too close to the corner, even with a large lobe, the water light density can still be insufficient. To avoid undersampling, we introduce adaptive camera passage theorem. First, we estimate the footprint of the sampling lobe, use the distance between the shading point x and the hit point y, PBSDF, which is the PDF of the BSDF impedance sampling, and the geometry term. Then, we can estimate number of water lights inside this estimated area by multiplying it with the water light density. Fortunately, we already compute the water light density per light for adaptive sampling elimination during our water light distribution process. Based on this N, the estimated water light count will make a decision. If N is large enough, we use the water lights that overlap with the hit point Y. If N is too small, we conclude that we do not have sufficient water light density, so we extend the camera path similar to path tracing. In addition, to avoid visible sharp changes from one sampling method to another, we use two parameters N minimum and N maximum. If the estimated count is lower than N minimum, we always extend the path. If it's larger than N maximum, we always terminate the path. Between N minimum and N maximum, we do both and blend the results. This is the result without passage theorem. You can see with passage theorem, most artifacts due to undersampling disappears. This image shows the average path length. As you can see, these are more bounces near corners because these paths need more watchlets to shade. We have finished introducing all the components of our method. Let's see some results. The first is the kitchen scene. Let's compare our method to rich VSL, using images rendered with the same number of virtual layers. Rich VSL take longer shading time than our preparation plus shading time. In addition, rich VSL also requires a much longer virtual preparation time. Still, our method produces clearly superior results. Compared to path tracing with MIS and LiveBVH, using the same shading time, our method can produce closer results to the reference. And if we give path tracing our entire computation time, our result still has lower noise. When it comes to a more challenging scene, the rich dot scene. Again, rich VSL takes much longer preparation time and shading time, but our result still has much less noise in this scene. It's not surprising, path tracing does not work well in this scene. Even with the same total time, our results has much less noise. The quality improvements or rich VSL can be attributed to the improvement of our virtual distribution. Compared with rich VSL, our method automatically places VSLs with a higher density where prominent specular reflections appear. In rich dot scene, because rich VSL generate virtualized on photon's position, only a few virtualized are placed inside the room. Our virtualized are generated from cameras, so we don't have the undersampling problem of other virtualized methods. In conclusion, we have introduced the virtual blue noise lighting that improves the indirect illumination estimation pipeline using virtualized. Unlike typical virtualized generation that relies on light passes, our method uses camera passes for virtualized placement. Then, we combine this approach with an adaptive sample elimination strategy that leads to a blue noise distribution with varying density. Furthermore, we describe a photon splitting method that can efficiently use a large number of photon passes for generating the emission profiles of virtualized. We combine BSDF sampling and power-based sampling with MIS to improve the illumination estimation from our virtualized during shading. Moreover, we have described an adaptive camera passation technique for resolving undersampling. You can find more details in our paper and supplemental document. Our project page includes a link to the source code of our implementation using a GPU ray tracer in Spherical. Thank you for listening.
Thanks for the presentation, Tianyu. So again, people, you can either step to the mic, or if you're shy, yes, we have Daqi, which
Can you hear me?
Hello, can you hear me?
Okay, yes, you can ask your question now. Yes.
Here is a demo of our render.
Oh, okay. So actually, I had a question, which two things weren't very clear to me during the presentation. So maybe we can start with the first question in the question board. In the adaptive sampling elimination, can you weight samples to reduce their chance of elimination for the specular cases?
Good. Do you mean the sample elimination stage can improve the performance of sampling specular effects?
Is it okay? Can you hear me, Tianyu?
Yeah, I can hear you.
Yeah, okay. So regarding the questions, is it fine to?
Sorry, do you want me to ask it verbally?
Yes, if you can.
Sorry, I was just watching. Obviously, I haven't seen the paper, but just watching the process, it seemed like you were subdividing the screen down and basically reducing the number of samples as you went down till you got to reasonably even density. But if you instead weighted your samples, can you reduce it down so it's not so much so that the sums of, I don't know how you would put it. I guess you'd have to have a reciprocal for the more important thing, but so the sums of each region came to be about the same. That way, if you have this case where you need more samples for something which is very concentrated, the specular stuff, it would automatically compensate.
Actually, what we do is adaptive elimination. So, so you can imagine in path space if there are high frequency paths. So basically, during our initial candidate generation, we will put more samples for where high frequency specular effects happen. So, and then we will compute adaptive Poisson disk radius. So, which can ensure us remain more samples for these places.
Okay. Oh, that's probably equivalent then. Okay, thank you.
Okay, so I have another question, which is basically when in the sampling density you showed, where we can see the samples after sample elimination, it seems that because you're doing a first bounce on the geometry to know where the light position will be, you will have some kind of acoustic of any specular material you will have, and so you have a higher density in regions that do not necessarily have high density for the lighting. I was wondering whether this is something that would help for performance-wise to solve or not, and if it is something that you've tried to compensate.
Yeah, that's a good question. Yeah, only considering BFDF sampling during initial sample generation can be not enough. So we have in our future work we want to try like gradient information and guided the initial candidate generation that can be more robust. Yeah.
So I want to add something. So actually, this strategy of tracing rays from camera to put VPLs actually works well for most things we tested. And maybe the issue you just mentioned, like caustics, actually, if the caustics is not really high frequency, then usually the camera VPLs generated from camera will still have a well enough a placement for capturing those caustic effects. So unless you have very high frequency caustics, which probably need the higher density of VPLs there. So for rendering those, maybe we want to kind of blend a strategy of also generating some VPLs from the light.
Okay, so my point was well that because you're sampling from the camera, you can have acoustic, but from the importance of the camera. Yeah. And this will not reflect the density of, like, it will be oversampling a region in space, but really doesn't need that much samples, contrary to the rough or the specular samples you need to add to better convey the acoustics.
Yes, but actually we've tested a lot of things, and we found that this camera generation, VPL generated from camera, actually provides very robust rendering quality in all sorts of scenarios. Yeah.
Okay. Thanks. So I had the last question. Basically in the rendering step, so the last step after the virtual point lights generation, you do VSLs sampling. Do you any specific sampling strategy like I I don't know, maybe a specific sequence for random number generation or something that improves the quality, or is just pure random? And I guess
we just use pure random for this BSDF sampling. Yeah, I haven't tried other things.
Okay. Well, thanks for listening, and I think we can all thank the speaker for this session, and move to the next one.
Have you ever wanted to see realistic ray trace caustics in real time, but you have no recent powerful GPU with hardware ray tracing support? Don't worry, here's an alternative way to render the ray trace caustics using only an image space technique. We introduced a bidirectional image space ray tracing, which basically traces a ray from a light first using reflective shadow maps, and then traces another ray from a camera using a G-buffer, just like we typically do in screen space reflection and refraction. And finally, we merge those trace paths using a denoiser. Take a look at the comparison between caustics mapping and our approach. You can see that our caustics have sharper edges and smoother intensity gradient. At the same time, we also achieve the caustics outside the light view that doesn't exist in caustics mapping result. Let us show you how our solution makes high-quality caustics affordable for everyone in the poster session. Thank you and see you there!
Eye-based point rendering is a new algorithm that combines the geometric parallelism of view-independent rendering with new eye resolution shading efficiencies throughout the pipeline to make real-time multi-view effects more practical. Standard multi-view rendering renders a scene 6 times per cube map, often requiring dozens of geometry traversals per frame and repetitive computation of lighting within each eye pixel. We demonstrate eye-based point rendering by applying it to dynamic cube map reflections. In a scene with millions of triangles and 20 reflective objects, eye-based point rendering generates 10 times fewer points than view-independent rendering and is over 3 times faster than multi-view rendering with comparable visual quality. Furthermore, our algorithm enables drastic speedups of recursive reflection without any additional pipeline paths or buffers. Visit us at the poster session to find out more. Thank you.
Imagination presents its new triangle bisection tessellation with fractional LODs as a superior alternative to existing methods. It uses per vertex tessellation factors rather than per edge. A patch is initially subdivided into one subtriangle per edge. Bisection is applied to all subtriangles when a tessellation factor exceeds a threshold. The new vertex inherits its own tessellation factor. The algorithm supports quad, triangle, isoline, or any polygonal domain. Vertices have fixed UV coordinates, ensuring stable geometry as tessellation factors change. Blending is used to provide fractional LOD support. A child vertex is assigned a displacement factor. Displacement factors are derived from tessellation factors of parent vertices. The displacement of a child vertex is given by interpolating between its full displacement and the average of its parent vertices. Blending can be performed for any attribute, not just displacement. Here is the modified pipeline with an optional hull shader and new fixed function blender. Thank you for listening.
Hello everyone, this is Chewy from Zhejiang University. I'm glad to present the solution of ray tracing denoise combined with super resolution. It uses only the RGB noise image and motion vector. It needs the geometry information like normal or depth, which reduces the bandwidth of rendering output. Also, the combined super resolution ability reduces the dominant computation as 1/4, which is estimated to about 40 gigaflops. We also analyze the blending and skip weights from the intermediate layers to verify our design methodology. One interesting side product is that the analyzed indicating that the segmentation backbone networks may benefit the ray tracing denoise task. Thank you.
We propose an adaptive extension of the Dynamic Diffuse Global Illumination or DDGI technique. DDGI is a probe-based GI technique that places probe on a regular grid and populates them with uniform sampling. With a fixed sample budget per frame, increasing the probe count reduces the number of samples per probe. As such, the technique fails to capture transient dynamic changes in a scene due to a less than desired concentration of resources per probe. Our adaptive extension aims at improving resource concentration in critical areas. We define several heuristics identifying the important probes, such as probe close to the camera and geometric surfaces, and probes recording a change in visibility and irradiance. We quantify the heuristics by tracing pilot rays and use multiple parallel Markov chains to sample the important probes. Our approach reduces lag and improves transient response to dynamic changes in the scene. Come to our poster to learn more.
We present opacity map compression for ray tracing. Modern APIs perform ray triangle intersection, but run a shader to do alpha tests, introducing latency. This can soon add up and be costly. But many tests are a clear hit or miss. We prefer these to be done early in ray triangle hardware. At HPG 2020, Gruen et al. Presented opacity masks. The mask has 3 states per region: fully opaque, fully transparent, or run the shader. Maps are accessed from barocentrics. No texture mapping is required. We propose using a square map per triangle pair. See poster for reasoning. Higher resolutions give better savings, but bigger maps use more storage and bandwidth. We use VQ compression. It's simple to decode and allows random access. With 2x2 vectors, we found uniform cases are common. We avoid storing these in the codebook and dedicate 3 indices. The data often has symmetries. We have 3 per quadrant transformations to reduce the number of unique vectors. Thank you for listening.
Hi, I am Dhaval. I am going to present learn transfer for surface geometries. Precomputed radix transfer is widely used method to obtain ray tracing effects for low frequency eliminations in real-time applications. It achieves it by disentangling the rendering equation into transfer and lighting and precomputing them individually. Most previous methods relied on mesh-based geometries, either storing transfer at vertex space or UV-mapped texture spaces, both inherently requiring a tabulated structure in the geometry. The main drawback of previous methods is it is not very easy to address geometries with no inherent tabulation, like SDFs. Hence, we propose to use transfer regressing neural networks trained in a supervised fashion, which takes sample data as input and regress the transfer values as output. We club the regress transfer at runtime with rule product formulation to obtain the diffuse and glossy renders. The geometry used here is SDF along with the network evaluation per fragment while obtaining real-time frame rates. Please check out our poster during the poster session.
Okay, so that was the end of the fast forward. So we are going to end the broadcast now. So for those of you who are following us on Twitch and YouTube, the video should be taken down soon. So we hope to see you tomorrow. And normally for those of you who are following us on OEA, you've all been moved to the poster hall, hopefully.